Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 2 on the Pythagorean Theorem and its converse. Now, in the last lesson we looked at the Pythagorean Theorem, and make sure that you're comfortable with that lesson before you go on to today's lesson. As we saw in the last lesson, our first one in Unit 8, the Pythagorean Theorem is a formula, essentially, that relates the lengths of the three sides of a right triangle. And let's review that right away before we start talking about what the converse of the Pythagorean Theorem is. All right, so what does the Pythagorean Theorem say? Well, it says if you have a right triangle, right, and the lengths of the two legs, the two that are perpendicular to each other, are given by A and B, and the length of its hypotenuse is given by C, then the following equation is true. A squared plus B squared equals C squared. Or, if you want to put it in terms of legs and hypotenuses, leg 1 squared plus leg 2 squared is equal to the hypotenuse squared. Now, as we saw in the last lesson, what the Pythagorean Theorem allows us to do is find any missing side of a right triangle if we know the other two side lengths, all right? Sometimes it's a little bit easier, like when we're missing a hypotenuse. Sometimes it's a little bit more difficult when we're missing a leg. But the Pythagorean Theorem can be used in both situations. So, let's take a look at exercise number 1. Given each of the following right triangles, use the Pythagorean Theorem to find the missing side. Both will be rational numbers. All right, I'd like you to actually pause the video now and test yourself. Make sure that you can use the Pythagorean Theorem to find this missing hypotenuse in letter A and this missing leg in letter B. Pause the video now and take a few minutes to do that. Make sure that you have your calculator handy in order to do some calculations today. All right, well, in letter A, we are missing the hypotenuse. So let's let this be 16. Let me change this to blue, maybe make it a little bit less thick. So let this be equal to A. We'll let the 12 be equal to B, and then what we're missing is the hypotenuse C. All right, so since it's a right triangle, the Pythagorean Theorem holds A squared plus B squared equals C squared. A is 16, B is 12, and we get that equal to C squared. Now, we talked about this a little bit last time. You can actually put that 16 squared plus 12 squared into your calculator just like that, and it will do all of that summing for you. You'll get C squared equals 400, and then in order to get the value of C, we need to take the square root of 400, which thankfully that's nice enough I can do in my head, and that's just going to be 20 inches. All right. Now, that was a situation where we used the Pythagorean Theorem to find the hypotenuse when we knew the two legs, and that is the easiest, most straightforward use of the Pythagorean Theorem. It is a bit more difficult when we know the hypotenuse, one of the two legs, and we're trying to find the other one. So let's go through that one. All right. Now, for me, I pretty much universally let the one that I'm looking for be equal to A if I'm looking for one of the missing side lengths, or one of the missing leg lengths, sorry. And then my hypotenuse in this case is always C. So I'm going to have A squared plus B squared is equal to C squared. All right. My A squared I don't know. My B squared is equal to 10. My C is equal to 26. Now in this case, I can't really use my calculator magic yet. I just have to literally work these things out. Let me figure out what 26 squared is. That's 676. And now is that extra little step of algebra I've got to do when I'm solving for one of the legs. I've got to get it all by itself. A squared is 576. A then will be the square root of 576. Let's do that on our calculator. Square root of 576 gives me 24. In this case, 24 meters. All right. So, right, when we know we have a right triangle, then we know that A squared plus B squared equals C squared. And given any two of those sides, A, B, C, just two of them, we can find the missing third side. Takes a little bit more work when what we're missing is one of the two legs, simply because we've got to do this little subtraction before we take the square root, but it's still pretty easy. All right, so let's move on and start taking a look at the converse of the Pythagorean theorem. Now, theorems are kind of like one-way roads, all right? Specifically, the Pythagorean theorem, if I've got a right triangle, then a squared plus b squared equals c squared. But the converse of the Pythagorean theorem tells us when a triangle is a right triangle based on the side lengths. Specifically, the converse of the Pythagorean theorem, if the lengths of the three sides of a triangle, not a right triangle, of a triangle are a, b, and c, where c is the longest side, and a squared plus b squared equals c squared, then it must be a right triangle. Now again, logic is a little bit tricky, okay? So keep in mind the Pythagorean theorem says if I've got a right triangle, then a squared plus b squared equals c squared. The converse of the Pythagorean theorem says if a squared plus b squared equals c squared, then I have a right triangle, right? So let's take a look at how that plays out in exercise number 2. Given each set of numbers below, could they be the sides of a right triangle? Justify using the converse of the Pythagorean theorem. All right, now one thing to have no doubt about. All right, in the Pythagorean theorem, the longest side, or the largest number of the three, has to be by itself. It has to be the c, right? So 28, 45, and 53, could they be the sides of a right triangle? Well, if they could be, then they'll fit the Pythagorean theorem. So how do I check that? Well, here's what I do. I take the two smallest ones, I square them, and I add them together, right? So I take 28 squared plus 45 squared. So let's see what that is. 28 squared plus 45 squared is 2,809. Right? That's my, if you will, a squared plus b squared. Now the question is, does that equal c squared? If the answer is yes, then these are the side lengths of a right triangle. And if the answer is no, then they aren't. It's that simple. So now let's check 53 squared. All right, so I come in here, I do 53 squared, I get 2,809, and so yes, they are the side lengths of a right triangle. And it's just a beautiful test, right? It tells you whether or not a triangle is a right triangle or not. It's that simple. If I square this, add them together, and then I check to see if it's the square of this number, and if they're the same, then yes, it's a right triangle. If they're not the same, the answer is no. So given that, what I'd like you to do is see in letter B and letter C whether these three numbers could be the side lengths of a right triangle. All right, let's do it. Here we go. So 17 squared plus 22 squared. Whoops, that doesn't look like a squared. Let's try that again. All right, lots of calculator work here just because we don't want to have to square these numbers by hand, not when they're relatively large. If they were smaller, it'd be fine, right? So that's 773. Now let's see if 29 squared is 773. That's 841, so no. Those could not be the side lengths of a right triangle. All right? It's really that simple. Now, the only thing you have to be a little bit wary about is here, these numbers are given in numerical order, meaning that they're going from the smallest to the largest. If for some reason a problem tried to get tricky on you, and they didn't give them to you in that kind of ascending order, remember, it's all about whether the sum of the squares of the two smaller ones is equal to the square of the largest one. Okay, so I would never want to do 17 squared plus 29 squared and see if it was equal to 22 squared. That would just never ever happen, right? It just couldn't. There's physically no way. Let's check it out in letter C. Let's take a look at 15 squared plus 36 squared. See what we get there. 15 squared plus 36 squared is 15, 21. Now let's take a look at 39 squared and see what we get there. 39 squared, also 15, 21, so yes. You don't always have to put the exclamation point down, but I want to be very clear that I'm excited when three lengths could be the side lengths of a right triangle. I'm excited, and apparently I'm also excited when they can't. I'm just an excitable person. All right, so it's that simple, and that's the converse of the Pythagorean theorem. Again, the Pythagorean theorem says if I've got a right triangle, then a squared plus b squared equals c squared. The converse says, hey, if a squared plus b squared equals c squared, then that thing's a right triangle. Now, again, the Pythagorean theorem is so important in math that we give a special name to three numbers that could be the side lengths of a right triangle. Any three whole numbers, so it can't involve decimals or fractions or anything like that, but any three whole numbers that could be the side lengths of a right triangle are known as Pythagorean triples, because there's got to be three of them, so they're triples. Anyway, they're often shown like coordinate points, except instead of like x comma y, it's like x comma y comma z or something like that. All right, so all a Pythagorean triple is a set of three numbers that could be the side lengths of a right triangle. And these things are so famous, like if you went on Wikipedia or something like that, or just onto Google and typed in Pythagorean triple, you'd find hundreds of websites devoted to them. There's an infinite number of Pythagorean triples, and they get bigger and bigger and bigger, and there's lots of study of them. Anyway, we don't need to go there. We just want to figure out whether each one of these sets of triples is a Pythagorean triple. Now, that really is no different than the problem we just did. I mean, I'm telling you, this is just 6 more of what we just did in exercise 2. So let's take a look at letter A, and then we'll have you work on the rest of them together. All right, in letter A, we've got the set 3, 4, 5. So is that a Pythagorean triple? Well, what I want to do is do 3 squared plus 4 squared. Now this one I can actually just kind of do in my head. That's 9 plus 16, and that's 25. The third one is 5 squared, and that's also 25. So yes, that is a Pythagorean triple. In fact, this might be the most famous of all Pythagorean triples. It's known as the 3, 4, 5 triple. All right, and it has nothing to do with them being consecutive integers. Trust me, 4, 5, and 6 is not a Pythagorean triple. 7, 8, 9 is not a Pythagorean triple, right? But 3, 4, 5 is, because when I take 3 and I square it, 4 and I square it, and I add them together, I get the square of the third number, 5. All right, so what I'd like you to do is go through each one of these, and in fact, again, let's do letter B together, all right, to show you how you can kind of speed up the process. There's absolutely nothing wrong with kind of just doing, okay, let me do 14 squared plus 22 squared, and see what that sum is on my calculator, right? I don't really need to figure out what 14 squared is individually, right? I can just do 14 squared plus 22 squared. I get 680. Then I look at 30 squared. I can do that one in my head, but just to be clear, 30 squared, right, is 900. And so, no, that is not a Pythagorean triple, right? Now again, if you're a little confused from our last lesson, right, where we were using the Pythagorean theorem to find missing sides, right, that always involved taking a square root. And notice, we don't have to do that in any of these, because all I'm trying to do is see if the three numbers make the Pythagorean theorem true, right? Do the two smaller ones when squared and added together give you the square of the larger one? If the answer is yes, these are a Pythagorean triple. And if the answer is no, well, then they're not. So pause the video now and go through the remaining 4 of these things and see which of the 4 are Pythagorean triples and which aren't. All right, let's do letter C. Here we go. I want 5 squared plus 12 squared. Okay, bring our calculator up. 5 squared plus 12 squared gives me 169. 13 squared, I know that one in my head is also 169, so yes, that is a Pythagorean triple. Now I mentioned that the most famous Pythagorean triple is probably the 3, 4, 5 triple. The second most famous one is our 5, 12, 13 triple. That one comes up a lot in problems. You'll see it in problems that we do in this unit, but just kind of a warning on that. Now let's look at some with some larger numbers. All right, let's take a look at this one. 48 squared plus 55 squared. That's where I definitely want my calculator. I don't want to have to do this stuff by hand. 48 squared plus 55 squared. That gives me, let me move this over, a little space, 5,329. Let's take a look at 73 squared. Let's take a look, 73 squared gives me 5,329. So you bet, that is also a Pythagorean triple. Let's just keep going on these. Let's take a look at our 18, 24, and 30. So 18 squared plus 24 squared. Make that look a little more like a 2. See what we get. 18 squared plus 24 squared gives me 900. And 30 squared is also 900. So yes, that is also a Pythagorean triple. Could be the side lengths of a right triangle. And my final one, 32 squared plus 47 squared equals, let's take a look. 32 squared plus 47 squared equals 3,233. Let's take a look at 57 squared. And I get 3,249. Close, but as they say, no cigar. So no. All right. But it's really that simple, right? And again, the difference between a Pythagorean triple and what we did in exercise 2 just doesn't matter, all right? This is just, a Pythagorean triple is just a technical name given to 3 whole numbers. They got to be whole numbers, no decimals, no fractions, nothing like that. 3 whole numbers that could be the side lengths of a right triangle. That's it. All right, let's keep going. Now, one of the really kind of cool things about Pythagorean triples is that any multiple of a Pythagorean triple will also be a Pythagorean triple. Now, we could actually prove that, but it involves some sort of advanced algebra that we don't really want to go there right away on. So let's take a look at exercise number 4, and let's just see how multiples of our most famous triple are still triples themselves. Take a look at exercise number 4. One of the most common Pythagorean triples is 3, 4, 5. See exercise 3a. Any multiple of this triple will also be a Pythagorean triple. Each of the triples below is a multiple of the 3, 4, 5 triple. Show that they could all be the side lengths of a right triangle. Now again, just to make sure you understand the idea of a multiple, right? Because you've looked at multiples of numbers for years and years, but you've never looked at multiples of coordinate pairs or triples or anything like that, right? 6, 8, and 10, all 3 of those are just double 3, 4, and 5. 9, 12, 15, all of those are just 3 times 3, 4, and 5. And 33, 44, 55, those are all just 11 times 3, 4, and 5, all right? And my claim is not just with the 3, 4, 5 triple, but any of them, like the 5, 12, 13 that we saw in the last problem. With any triple, if you multiply each one of the numbers by a whole number, or actually by any number, the resulting triple will also be a Pythagorean triple. So let's see how that works, right? So for 6, 8, 10, right, this is just twice 3, 4, 5. If I do 6 squared plus 8 squared, right, on my calculator, simple enough. We could actually do this one without the calculator, but we're in the groove here, right? 6 squared plus 8 squared is 100, and 10 squared is 100. And so, yeah, that's also a Pythagorean triple, right? Because a squared plus b squared equals c squared. Why don't you verify now that both b and c are also Pythagorean triples by doing the same procedure? All right, back at it. Let's take a look. Right, for letter B, we're looking at 9 squared plus 12 squared. Let's see what we have there. Right, 9 squared plus 12 squared gives me 225, and 15 squared is also 225. So you bet. And finally, right, 11 times our original triple. These numbers will get a little bit bigger. 33 squared plus 44 squared. Let's see what we get there. 33 squared plus 44 squared gives me 3,025. And 55 squared, let's take a look at that, gives me 3,025. All right, the moral of the story is, if you had any triple whatsoever, like for example, if you had the 5, 12, 13 triple that we looked at in the last problem, and let's say that you took each one of these numbers and you multiplied them by 5, right? That would give me 25, 60, and 65. What you would find is that this is also a Pythagorean triple. All right, as long as each one of these numbers gets multiplied by the same thing, the resulting triple would also be a Pythagorean triple. It would also work the other way around. If this wasn't a Pythagorean triple and I multiplied each one of these by the same number, this also wouldn't be a Pythagorean triple. All right, let's finish this up with one last problem. Strangely enough, the converse of the Pythagorean theorem is used all the time in construction in order to ensure that right angles occur. And let's take a look at kind of a classic situation in exercise number 5. On a construction job, Christoph wants to join a 12-foot long board with an 8-foot long board so they make a right angle with each other. He can do this by making sure the diagonal from point A to point B is what length? Round to the nearest tenth of a foot. So you could imagine, right? You may have even worked with boards before, right? Where you connect them with a screw or something down here, and there's a little bit of play, right? And you want to make sure that maybe those two boards form a perfect right angle. So the question is, if you then had some kind of a ruler, right, and that was an actual straight line segment as opposed to a little bit of a curvy line segment, how long should it be in order to ensure that that's a right angle? Pause the video now and see if you can actually use the Pythagorean theorem to help you figure out what that length would need to be to ensure that that would be a right angle. All right, well in this case, we're actually using the Pythagorean theorem. So I'm going to call this C, okay? And I'm going to say, well, if I've got 12 squared and 8 squared, I need those to add together and be C squared in order for this to be a right triangle. So simple enough, I'm going to say 12 squared plus 8 squared. And that's going to give me C squared is equal to 208. And then I'm going to take the square root of 208. And I'm going to move this out of the way so I've got a little bit of room. Square root of 208. And that should be, what do I want? Rounded to the nearest tenth of a foot, 14.4 feet. So you can see this, right? You're out on this construction site. You want these two boards to be perpendicular with each other, but maybe you don't have any kind of thing that will give you a right angle, right? So you work out the Pythagorean theorem and for this to be a right angle, then a squared plus b squared has to be equal to c squared, right? So what does c squared have to be? It's got to be 14.4. So you take your tape measure out, right? You have one person sort of adjusting this angle until that length is exactly 14.4 feet, and then we know that will be a 90-degree angle. All right, let's summarize. Now, the difference between the Pythagorean theorem and its converse is very, very subtle, right? The Pythagorean theorem says if I've got a right triangle, then a squared plus b squared must be equal to c squared. And I can use it then to find missing sides of right triangles. On the other hand, the converse of the Pythagorean theorem allows you to say, well, if I've got 3 sides of a triangle, is that triangle a right triangle? And it will be as long as a squared plus b squared, as long as I take the 2 smallest sides, square them and add them together. If that gives me the square of the largest side, I've got a right triangle. And if it doesn't, then I don't. It's that simple. All right, well, we're going to be using both the Pythagorean theorem and its converse in future lessons. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.